So to sum up the implications of dual band cell planning that we need to do for 802.11n, the first conclusion is that one cannot optimally cell plan for 5 GHz and 2.4 GHz together in a microcell environment. Second conclusion is that the microcell planner has to focus on 5 GHz, which means that the 2.4 GHz band will have even higher than normal co-channel interference. The bottom line is that legacy users get a bad deal. The problems of cell planning for 5 GHz and 2.4 GHz simultaneously, along with the need to reserve the 5 GHz band exclusively for end clients, means that introducing 802.11n into a microcell environment is a much harder cutover. Legacy clients are relegated to the 2.4 GHz band and may feel the impacts of increased co-channel interference in that band. The channel blanket, on the other hand, enables a gradual introduction of 802.11n into an existing business environment. Legacy clients can operate on 2.4 GHz or 5 GHz, and both bands are also viable for end clients. When introducing 5 GHz operation into a channel blanket, there is no need to do cell planning, and the only thing you should do is tighten up the AP spacing somewhat to optimize aggregate error rates that clients experience. This doesn't require cell planning algorithms at all. Now let's take a closer look at rate versus range, which we touched on earlier. The expression rate versus range describes a very basic fact of wireless networks, that the available error rate drops off rather dramatically as the client distance from the AP increases. So users need to be near an AP to get good error rates, otherwise the potential of 802.11n is wasted. The chart in this slide shows the steep drop-off in rates as one gets further from the access point. At only 15 meters from the access point, the error rate has decreased to only 1/3 of the maximum error rate. The implication is that the denser the AP deployment, the better the aggregate throughput of the wireless LAN, or conversely, an overly sparse placement of APs can nullify the benefits of 802.11n just like legacy users can. The question is, do the microcell and channel blanket architectures support denser AP placement? Well, we already know that the channel blanket works well with dense AP placement because there is no co-channel interference. However, the microcell architecture, which suffers from co-channel interference, cannot tolerate dense AP placement. So let's see what the difference is between a microcell deployment and a channel blanket deployment with just a slightly denser AP placement. In our use case, there are 6 active clients on the floor. As we saw in the rate versus range discussion, the throughput of these clients will depend on how close they are to the nearest cell. In the microcell deployment above, you can see that only 1 client is close enough to the AP to get a high error rate. 2 get a moderate error rate, and 3 clients actually get a very low error rate. Now, because the channel blanket does not suffer from co-channel interference, we are able to deploy an additional 4 APs to create a denser AP deployment. The impact is significant. Instead of 4 clients having low error rates, only 2 have low error rates in the channel blanket deployment. The rest get moderate or high error rates, so the average error rate provided to clients in this channel blanket deployment would be significantly higher than the average error rate in the microcell deployment shown previously. So the aggregate throughput of the channel blanket would be far superior. If even higher throughput is desired, more APs could be added to the channel blanket so that all clients get at least a moderate error rate. Another deployment issue has to do with one of the underlying technologies of 802.11n called MIMO. MIMO is another contributor to the almost impossible challenge of microcell cell planning in an 802.11n environment. MIMO causes unpredictable RF propagation and longer range propagation at lower error rates, so cells become larger and less predictable in shape, as shown by the jagged shape on the right side of the screen. So 802.11n actually gives two cell planning challenges. The first is the need to simultaneously deploy the 5 GHz and 2.4 GHz bands. The other challenge is the unpredictable cell shape caused by MIMO. (802.11n) supports high bandwidth mobile devices, so there is also another important challenge we have not discussed, which is roaming. As we can see in this slide, while roaming in a microcell architecture, the client will likely move through several cells. While moving between any two cells, the client needs to disassociate from the first cell and then associate to the cell it has moved closest to. This process can be further lengthened if there are security policies that require authentication with a radius server, for example. As a result of this, there will be many dropped VoIP calls. In contrast, in the channel blanket architecture, the client is associated with a switch. No cell disassociations or reassociations are needed as the client moves around the channel blanket because it stays associated to the WLAN switch.